Welcome. In this lesson we'll build the 3 coordination topologies you'll reach for again and again when building multi-agent systems in LangGraph: the supervisor pattern, hierarchical teams, and parallel execution. By the end you'll know how to route tasks dynamically, nest agent teams, and run work concurrently while safely merging results. Before any pattern, understand state. Every LangGraph application defines a typed state object that flows between nodes. Each channel can have a reducer, a function that merges incoming updates. The messages and results channels here use operator.add so updates append instead of overwrite. This becomes critical the moment 2 parallel nodes write to the same key. Without a reducer you'll get a conflict error. The supervisor pattern centralizes decision-making. A supervisor node, usually an LLM call, reads the state and returns a routing decision, which worker should act, or finish. Conditional edges map that decision string to the corresponding node. Workers route back to the supervisor, creating a loop. This gives you flexible routing and a single point of accountability, but always add a recursion limit so a confused supervisor can't loop forever. As your team of agents grows, one supervisor's prompt gets bloated and slow. The hierarchical pattern divides workers into specialized teams, each governed by its own sub-supervisor, with a top-level supervisor routing between them. In LangGraph this is elegant. A compiled graph is itself a node, so each team is a subgraph plugged into the parent. Just make sure state schemas line up at the boundaries, or transform them explicitly. When subtasks don't depend on each other, run them in parallel to cut latency. Adding multiple edges out of one node makes those targets execute in the same superstep. A downstream aggregator node only fires once every incoming branch finishes, a built-in synchronization barrier. Because each worker appends to a reducer channel, their outputs merge cleanly. When you don't know how many branches you'll need until runtime, the Send API spawns n parallel copies of a node dynamically. The Send API is the key to dynamic parallelism. Instead of hardwiring 3 branches at build time, your dispatch node returns a list of send objects, 1 per task. Each send targets the same worker node but with its own payload. LangGraph runs them all concurrently and merges results through your reducer. This is the classic map step of a MapReduce workflow inside a single graph. These aren't competing choices, they compose. A very common production shape is a hierarchical supervisor whose teams internally fan out their work in parallel. My advice: start with a single supervisor, measure latency and accuracy, and only introduce hierarchy or parallelism where the data shows it helps. Premature complexity is the enemy of debuggable agent systems. To ship these patterns, mind the production details. Always set a recursion limit to tame supervisor loops. Use reducers on every channel touched by parallel branches. Attach a checkpointer for durability and to enable human-in-the-loop pauses. Trace each node with something like Langsmith so you can see why the supervisor routed where it did. And remember, parallelism cuts wall clock time but increases concurrent token cost. Budget accordingly. To wrap up, master the state model with reducers first, because it makes every pattern work. Use the supervisor for dynamic routing, hierarchy to scale across teams, and parallel fan-out to reduce latency. Combine them intentionally and instrument everything. Next, build a small supervisor graph, then refactor it into a hierarchical, partially parallel system and compare the traces. That hands-on iteration is how these patterns become second nature.